Hello everyone, welcome back to another video on Learning Glass. Today we will do a problem on diffusion, particularly considering the time-dependent case, and you can get an analytical solution for a domain with semi-infinite medium. What does that mean? It means that while the transient means that you have this term dependent on time, some accumulation or depletion over time, then you have, we're going to consider it one-dimensional, call it z, where this goes to infinity, from 0 to infinity. And this is a partial derivative here because the profile, the solution, depends on time, and it also depends on where you are in the domain. In this case, one-dimensional. So this would look something like maybe a wall or something with some source of a concentration of some particular, let's call it a species, at the wall located at z equals 0. So if this is a mixture, call it with a binary mixture of A plus B, the question is, what is the concentration of A as a function of space and time? And here, it's a relatively simple case where at the far stream, this is called it's just some original concentration everywhere throughout the medium downstream. So there's some surface concentration, it's going to be higher, and over time it starts to evolve and it approaches this original far stream concentration of the mixture. So another way to say this, because it's dependent on time, to solve this differential equation, we have to specify an initial condition to constrain the solution. That would be that at z equals 0 and t equals 0, so initial t before time starts, at t equals 0, the concentration everywhere for all z but at time 0 equals this far stream concentration. So before you start the time, you have this uniform concentration of this component specified here for all z. The concentration, original concentration for all z. Then, so that's for the time, and then at the spatial boundaries, you have the surface in one dimensional, and then you keep on propagating out in this one dimension all the way to infinity. So the boundary conditions at the surface at z equals 0, the concentration at 0, z equals 0, nt equals, let's call it a surface concentration. Concentration of surface as time progresses. So the surface concentration at z equals 0, and then what we're going to do is that this surface concentration is going to be greater than the original concentration. That's how it will be a driving force or driving mechanism to diffuse from the surface outwards, because there's a concentration gradient from high concentration to low concentration. But we're going to assume that the penetration is relatively short. So we have infinity going this way, but the surface concentration doesn't get that far. or there's it doesn't take that much distance for it to approach this. So at z equals infinity, we're not saying that CAS, or yeah, eventually it starts off that the surface concentration is Ca0. That's why it diffuses. But Ca at infinity for all time equals Ca0 for all t. So including 0, that's the initial condition, but the concentration approaches this original concentration if we get far downstream enough. Okay, so that's the physical setup of this. It depends on time. The concentration profile in space and time changes, and it's defined by this initial concentration in the domain and the surface concentration. So let's write this balance of the species. It can accumulate or deplete in time. It can propagate in 3 dimensions, both by bulk flow and by diffusion. So the way that we wrote that was first starting off by this general balance, saying that it can depend on time. Then it could also have different fluxes in different dimensions. So this would be that flux in the x direction, the flux in the y direction, and the flux in the z direction. And then there can also be a source term where this particular species can be produced over time or per volume. So in this particular problem, we're saying it's one-dimensional. It does depend on time, and we're not considering reactions. So here, we're going to say no reactions in this particular analysis, and then it's only 1D here. Let's do the z direction. Let's keep the z direction, or I'll keep that. Let's pretend I crossed out the x, and let's focus on z here. Pick your dimension, we picked z. So that would give us that for this particular form of this conservation equation for species A, so that's the equation. The question is, what is this flux? Well, if we remember, the 1D flux of species A is in one-dimensional, depends on so this is n, the molar flux. It's not the mass flux, it's molar flux. That's what depends on the mass fraction times the total flux. This is the bulk motion. It's taking some of these species minus some diffusive flux. If it's a binary mixture, it's just a binary diffusivity. And you also have this contribution of the concentration gradient driving that. Choosing Z here. So here we're specifying no bulk diffusion, no bulk motion, only diffusion, only this molecular collision driven transport. Okay? So that we can plug into here. That will give us this second order differential in space with the addition of this time variable. So plugging that in here, This becomes a minus here. And we'll bring the diffusivity out. Equals 0. So here's our differential equation we're trying to solve. It's a function, it's a differential in time and a differential in z, in space, one-dimensional space, but it's a second derivative there. So this is the differential equation we're trying to solve. It's in 2 dimensions, so that makes it a partial differential equation. So partial differential equation, aka PDE, and so the question is, how do you solve this particular PDE? So how do you solve PDEs in general is you pretty much have to use, it's a case-by-case basis for the most part. There's pretty much no general rules on how to solve differential equations. Each one is a beast in itself. Each one opens up a whole can of worms. It's a case by case. Some of them, there's some family of them, and there are families. So the question is, which family or which strategies does this fall under? Well, this is a classic engineering PDE, as a matter of fact. It's this second order in space and time, one order in time, and there's a well-known approach. In general, these time-dependent PDEs can use this strategy called Laplace transform. But before we go and solve, well, let's convert these units or this variable into a more convenient. So let's define a convenient variable. Let's call it phi, and it's just the actual concentration you are. Let's call it phi is the actual concentration minus the far stream concentration. When you do that, you get a different boundary of different differential equation, similar but different. This differential equation becomes, I'll bring this spatial derivative to the other side. So it's still a partial differential equation, except that we just simply we just included this boundary condition inside of the variable here. And then, but when you do that, the boundary conditions get a little more simplified. So in terms of phi, you can say now that this theta at z and time equals 0 equals, you just plug in that concentration at 0, which is Ca0 minus Ca0, which gives you this theta equals 0 now, because we shifted it in terms of this formulation. And then similarly, that would be the initial condition, but then the surface concentration for all time stays the same, Cas minus Ca0. It's the same, except we're always including this boundary condition here in this variable. And then for the infinity, It's the same, CA0, CA0, this also becomes 0. So this becomes just a more convenient way to include these boundary conditions here. Okay, so now how do we solve this? What we have here is the concentration expressed in terms of theta, the actual concentration in the space and time relative to this far stream constant concentration. So how do we solve that? Let's keep this for now. D squared so now that we have these boundary conditions here, how do we solve that? Well, what we have here is a second derivative in concentration and of concentration with respect to space, and a first derivative in time. Well, the way to solve these is to use a Laplace transform. What is a Laplace transform? It uses like a mathematical formula to convert time space into S space. When you apply this equation operator, this mathematical operator, onto different situations, the net result, the main point of doing this for solving PDEs is to convert partial differential equations into ordinary differential equations. So you pretty much remove the time variable and convert it into some constant S by using this transform, this operator, which simplifies this two-dimension, or like this multivariable PDE, into one dimension. So that's what Laplace transform does. So Laplace is part of engineering and math and statistics. So it's a partial differential equation solving strategy. What you do is, by applying this, you go from this multivariable differential equation to ordinary differential equation, meaning single variable. And what you do is you go from time space, time variable, space meaning the variable, to S, Laplace space. Laplace space is called S space. So this would be the PDE. And then once you have this ODE, you solve the ODE to get a solution. And then once you have the S solution, you can go back to time space. So it's time space and Z space in this case. So we have both the variables time and Z. What I mean by time space is that your variable is time, and your solution depends on time. But that's what the special thing for Laplace. We're still staying in the Z space for this strategy, but this would be the final solution here. Like the actual tangible, real variables that we can work with for engineering. So it's common for statistics, engineering, this PDE, and occurs in many situations of engineering: heat transfer, mass transfer, momentum transfer, and different situations in statistics. And so what we're going to do here is we're going to go for the Laplace, the particular transforms we're going to do, time space and S space, is whenever you have a derivative, in this case it's d theta dt, the transform for this is some constant S times the function theta minus f of 0. In general, this is going to be 0 in this case. Then the other one is we're going to apply is whenever you can do a Laplace transform of the constant 1, that gives you 1 over s. We're going to use both of those right now. So that's the strategy. Then when we apply these transforms, it's going to greatly simplify this partial differential equation into just a differential equation in z. Okay, so let's plug those in right now. So we started off in concentration space. We just converted it to this simple theta variable just to make these boundary conditions a little easier. Then we're going to do a third transform going from theta space and t and z space into Laplace space, this s. And when you do that, the Laplace transformation becomes, instead of having this derivative in time, first derivative in time, it becomes s times the function of theta. Let's call it a new function, which is just in term function of z now, equals so it's still the second derivative, but so this is 0. In this case, it's 0. So this is our differential equation now. Now, this boundary condition here so this would be the BC in theta space. The BC in theta prime or theta bar would be 1 theta bar at z equals 0. You're applying this transform here. It's just the same thing over s though. Or z equals 0. I'm applying this one here. Z equals 0. CAS minus CA naught over s. And then for z equals infinity, that's still 0. We don't have this do this time derivative anymore. So by using this Laplace transform, we've got rid of the time space. We just replaced it with this s variable. That makes it one-dimensional now. I mean a one-variable differential equation. Then we transform the boundary conditions to the s space. And now we can solve this. So let's solve this equation. So now that we have an ODE, that makes it a little easier. So because we had a PDE, we had to find a strategy to solve it. In this case, the strategy was to convert it to a one-dimensional, one variable differential equation by using Laplace transform. Now we have this one-dimensional differential equation. How do we solve it? Well, that's another question. The solution is to look it up. this one, the function of, what this is, yeah. So it's the function equals the second derivative. In this case, the solution is, by looking this up, that the function that will give this solution is theta bar for z in S space. That's the function we're looking for that satisfies this equation, equals, in general, a, some constant of integration, times the exponent of plus S over the diffusivity times Z plus another constant minus so this function, if you apply these operators to it, will give you this, satisfy this differential equation. The next question is, what are these constants? Well, if we apply these boundary conditions to it, what that would give you is that to satisfy this boundary condition at infinity, so this is at infinity, this has to go to 0. Well, the only way to satisfy this boundary condition with this equation is that A has to go to 0. So this term is not, in general, this is the equation, but for these boundary conditions, this term has to go away to satisfy the boundary condition. Then B, to satisfy this boundary condition, B has to equal, is related to that boundary condition. So B equals CAS minus CA0 over S. So this is the general solution to this differential equation. Applying this boundary conditions gives you more specific. So the solution in S space, applying these boundary conditions, is okay. Are we done? No. We just did a lot of work. The whole goal is to solve this partial differential equation. Again, we applied the mass while we first converted it to theta space here. It's just a shift in terms of the boundary condition in the physical realm there. Then we used Laplace transforms to get this differential equation. And then we got a general solution by looking up our tricks up our sleeves of differential equations, ordinary differential equations. Then applying the boundary conditions in S space gives us this particular solution for this boundary conditions. Okay, but this is S space function. What do we do now? Well, let's go back to the inverse. Let's apply the inverse transform to go back to our original time domain. Inverse Laplace transform, that will give us the function we want. We want theta, which is the concentration shifted by the far stream concentration. So this function of z, space and time, equals I might have space. So the inverse Laplace transform of this is given by something called the error function. I don't know if you guys heard of the error function, but it's this thing. So this is our solution here. The concentration in theta space is related to the error function. What is error function? Error function, similar to the Laplace, it comes up in statistics, it comes up in engineering PDEs. It is some particular function So what you do is you either, it comes up in statistics, PDEs. To solve it, you use tables to find this, of the number value of an error function or approximations. There's some equations, some analytical equations that allow you to solve this in here. So, okay, so we have our solution in theta that we use by using a Laplace transform to get to the one-dimensional, one variable differential equation, ODE. Then we got a general solution and applied boundary conditions to make a specific function solution. And then we had that solution in S space and Z. Then we applied an inverse Laplace transform to get back into the time domain. That's this equation here. Let me write this in terms of the original concentration variable here. So this is in the Z space, the theta space. So CAS, the surface, minus this actual concentration that we want as a function of space and time. So this is our solution here. So this is what we wanted. This equals this here. It depends on the error function. Okay, now we can actually fill this in. How does this look? Well, if this is the z-axis here, let me make this into a proper graph here. So if this is not the wall, this is the wall. This is the wall, but this has a axis of concentration Ca as a function of z. This is z. Let's call this going approaching infinity here. And this is 0. So what the solution saying is that, let's call this CA0, surface, CA surface. This is a surface concentration. Let's call this level here the far stream concentration. And what this equation looks like is we're taking slices in different, fixing a time at one snapshot in time, this what the profile of Z would look like. So at the surface, it has to equal the surface concentration. Then it will not penetrate that far, and it will approach the surface concentration. So everywhere at the in space, it's Ca0. It's just slightly different due to the surface concentration. Let's call this T1. At 0, this is Ca concentration here, and then everywhere else it's flat. It's this far stream concentration before time starts. It's this level. Then when we allow time to go, it's going to penetrate slightly at this level here, and then over time it's going to penetrate a little bit more like this, but then still approach this free stream level. So these are different snapshots in time. So as you go in time, it's not going to, it's just going to keep on stretching out like that over time. So that's what the solution looks like. It never completely engulfs this whole region. It'll just keep on like asymptoting out in space, just stretching out. And that gives this analytical function that you can look up in tables or use an approximation to get a number. There's various things for the error function. Okay, another property here is what is the 1D flux at surface? Z equals 0. So what we're asking is the flux of A at Z equals 0 . Well, the flux, only due to diffusion, no bulk motion, is this diffusivity and the concentration gradient at the Z equals 0. Well, if we analyze this function here, this concentration, the derivative of Z is based on the error function. If we take that derivative, what we would get is that this equals, let's see if I can fit it in here. This equals negative DAB the difference here so at the surface you would get so that would be the flux at the surface. So here's the solution to the profile. The concentration profile in space looks like this, and then at increasing times it'll stretch out. So it's two variables. Here we're just showing a slice in time, and so we have three different slices here. Here it's just some fixed time. It looks like this in space. Then if you increase the time, this slice will look like this. So it's capturing this two-dimensional function in slices here. Instead of doing a 3D plot, it's doing a 2D plot with different contours of each time slice. So that is how you would solve this PDE of this mass balance of one species in one dimension. The boundary conditions give rise to this concentration difference where you have a surface concentration and this far stream concentration that you asymptote to. To solve this PDE in time and space, we had to apply Laplace transforms, and giving us this Laplace space solution here, applying the inverse transform from S space back to time space gives you this error function here, and giving you, going back into this concentration profile that we wanted here, we have this error function that looks like this in 2D with these slices here, and that also you can get the flux at the boundary here going into the domain. So that is an example of a specific mass diffusion problem, and we'll apply some examples like this over time as well. Okay, thank you. See you next time.